Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Future Friday, we're gonna talk about flawed energy solutions. So let's dive deep into it. So what's the core of it? Why do we need this much discussion on energy storage? Well, reality is energy storage is a must for cheap and abundant power. Now, many times people are like, "Oh, what if we have coal and all that?" No, we'll still need energy storage, especially if modern world wants to grow. We are reaching a point where that is compulsory. How compulsory? In 1950s and 60s, people started to get nuclear fever. In 60s to 70, people started to build nuclear power plant. In 70s to 80s, they realized they needed a pumped hydro energy storage system, because without it, they were stuck in a paradox, meaning you had to build power plants for that maximum power draw that happens, let's say, one time a day, like for 1 hour, let's say that evening time. That's maximum power draw. But here's the most of the time, the energy draw is not that much. But if your nuclear plant is designed for that kind of output, it's going to cost ludicrously large amount of money. And if you run it at downclocked position for very long duration, you're losing money. So they were like, okay, what can we do to solve it? Well, somebody was smart in 1977. They're like, okay, what if we build a nuclear power plant with the base load, right? We know for a fact that bare minimum this much power will also be consumed. Okay, we figure out the base load. Then we go above it. So let's say base load is 1500 megawatts. We build 2000. Now, like, okay, that gives 500 surplus. But here's the deal, that spike is 3000. So you store that surplus above the base load most of the time. And when you need that surge, tada, you discharge this puppy and you run power. Now, that's why we built pumped hydro in the first place in 1977s. So if you want cheap and abundant power for national growth and for safeguarding nature, you have to have it. There is no two way around it. And be mindful, we are trying this technology of like energy storage in different mediums also. For example, many countries have this idea like we have hydro dams. Cool, awesome. But that means they are a bit seasonal. Sometimes they could give you excess power for, well, they have excess power. What the hell you to do at that point in time, especially in rainy season? They're like, okay, what if we dump that much excess energy rather than just disconnecting it? We dump that energy into aluminum. So aluminum smelters were like basically they are in contact with power dispatchers, and power dispatcher will tell them, hey, some excess free power is coming in, fire up all the aluminum smelters. So we have to do this. This is not something, oh, fossil fuel does not have this issue. We always had this issue. We have to solve it. And if you want nature to survive, you have to switch into solar, wind, geothermal, geotidal, whatever have you. But all of them will require it. So there are many systems. Basically, when you're talking about energy storage, it's an umbrella term. It's almost like cancer. Cancer does not mean one thing. It means many things. So same goes with energy storage. It's an umbrella term, and many methods will give you some pros and some cons. You have to balance them out based on your specific requirement. So what's the core aspect? Where we focus right now? Right now we focus on duration. That's the key essence of it. So durations are generally classified in few broad categories, so to say. So you have 4 hours, days, weeks, and month. So let's start. So you must have seen Elon Musk, like how we can build a 100 megawatt hour battery like this quickly and all that. So what was that? Was that a grid energy storage? No, it was grid stabilizer, meaning if you have energy storage capacity for 1 hour, you can ride the peaks, so to say. Like peaks will happen, and if you do not have the energy storage to ride through the peak, you have two options. Either you disconnect everything or you let the frequency go down. Frequency go down is not an option. Let's say 50 hertz is the frequency. I don't think even you can drop to 47 hertz. If it goes below that, almost all generator circuitry breaker will like, okay, I'm out. All generator. That's what we call cascade failure. So you can understand that you have to disconnect a load. Or if you have energy storage, you dump excess power from that, or basically stored power from that puppy to smooth the grid. So we call grid stability. That is 1 hour. If you can withstand the oomph for 1 hour, that's basically used as a grid stabilizer. Then you start to push it to 4 to 8 hour zone. Now this is the sweet spot. This is what India needs at this point in time. This is what we call peak power shifting, meaning you take California's duck curve. What does that mean? That simply means it's the same thing everywhere, that during sun time you get GG amounts of power, but you do not have that much power draw. You don't. And be mindful, especially if hundreds and thousands and millions of households have solar home, they also reach a point where everybody is dumping so much excess energy into grid. Grid has to do what we call power curtailment. So you store that energy. When do we need that energy? The moment sun goes down, the moment people start to return to their household, the power draw spikes. Now, if we can smooth that spike, we're done. We're good. We sorted. Humanity is saved. We just need to smooth that spike. How much? 4 to 8 hours. That's the sweet spot. If we can smooth that out, done. Like renewable, we good, we got this. That's the sweet spot. That's where we are focusing right now. What about if you push it further? Let's say instead of 4 to 8 hours, you have like 16 hours, 32 hours. That we reach into what we call microgrids. Now, microgrids are really amazing technology. It's more of not amazing rather than clever technology. Many people in African nations realize they do not have the money to build a national grid. And the places that have national grid, it's almost collapsing, like South Africa, so to say. So they created a very clever solution. They built solar farms. Cool, awesome. Every individual they try to do it, it will not be cost effective, nor it will be powerful enough. So everybody pools their money. They built a solar farm. They put small amounts of wind turbine. They put a backup diesel generator, and then they have a giant battery as big as they can afford. Now, this microgrid, this is not designed to run a country. This is not designed to run a civilization. It's only designed to take care of a village. And they also have priorities on that. For example, medicine stores, medical clinics, those things, priority one. No power cut will happen to them. And then that's how you prioritize it. So now everybody gets energy without any hassle, without any pollution. And it's surprisingly cost effective. And many communities, even in Canada and in America, are doing this, where they have giant solar farm, they have giant battery banks, and they have one backup generator because, there are some bad days. And again, that system is very common in India also, because the place I live in has really bad grids connected. Grid stability is like lol. It's bad. It's bad. Let's just put it that way. It's bad. So all the petrol pump owners, they had to burn a lot of fuel just to run the power plant, because again, petrol pump does have a heavy power draw. So they were like, okay, what if we disconnect the grid? We are paying commercial fees, all that jazz. It's very expensive. What if we heated that, put as big of a solar farm as we can? They put that, and they have a battery bank. They still have the generator. So instead of generator running, let's say 200 days out of 365, now it's only running few days, especially in rainy season when you do not get enough sun. And again, if you have to do shutdown maintenance on solar, then you run on generator. So it's one of those things that once you can reach that point, basically you can go through 1 or 2 days of bad solar, done. Like this makes microgrids and renewable energy super easy. Then you touch 128 hour, that takes care of all humanity's problem. At that point in time, wind, go YOLO. Because we know our current analysis and last 10 years of data predicts that, that if we can store energy for 100 hour, grid level energy storage, we good. We good. We could. Like you must have seen, like Netherlands at this point was crossing 90% of its energy. And then what happened after time? We did not have storage. We basically are reaching a point where we are hampering our progress because of curtailment, not because of, oh, we do not have solar, we do not have, we have it. It's just that it has its own mind. So once you can have that point sorted. And now there is a hypothetical scenario which we call seasonal storage. I have not seen any technology that truly scales to that level. But if that happens, problem solved. Like at that point, humanity will start to grow outside of planet. It's like, yeah, in the rainy season, we had so much surplus, let's say hydro energy. Okay, we store it or we use it. Use it for metal or store it. Okay, cool. We have surplus wind in this season. We store it. You keep storing it, keep storing. And now you can handle anything that nature can throw for you. Anything. Like at that point, anything is manageable. So that's why we have to really focus on duration. So right now, sweet spot is 4 to 8 hours. The moment you cross that, majority of humanity's current problem will be sorted. Now, all systems have some flaws. Let that be very clear. You cannot build a system that's like, me good, me no problem. For example, pumped hydro, the most robust, the most time tested. We have been testing it from 1977. Longest lasting, many of them are still working and they're getting refurbished, upgraded. Their efficiencies are going up. So we know this works, but it does have poor round trip efficiency, meaning at best you're going to touch 70%, meaning you dump a 100 megawatt hour into it, you will get 70 megawatt hour out of it. 30 would be poofed. So you do need a bit of price differential to work. This is my personal favorite. Again, it has the most easiest smooth operation. You take an old coal power plant, you heat the boiler, dump this puppet, graphite blocks. Now, super easy, much cheaper than this, because again, this is the most amazing technology. It does have too much bureaucracy and red tape. And again, anytime you are touching water, you do have to go through too much bureaucracy. It never actually is growing as fast as it needs to. This does not touch it. It's just like, hey, it's a graphite block. Who cares? No smokestack, nothing. Cheap and easy. Take it and go. What's the penalty? 30% efficiency, meaning you dump 100 megawatt hour into it, you are barely going to get 30 to 35 megawatt hour out of it. Now, is that good enough? Well, if we are reaching into that 4 to 8 hours period, yes. Because again, that peak time power is so expensive for the grid operator, you would have no idea. Like core power plant, 1 unit for X price. Jet power plants that we have, you're running jet engine running on natural gas as a peaker power plant, yeah, that's multiple X compared to coal power plant. So every time during that peak they have to turn on that system, they pay exponentially more. This is like, bro, we stored that energy cheaply and we are dumping it 30% of it during high prices. It's like buy when it's low, sell when it's high. It's basically stock market, and it works, and it does add grid inertia and all that. This also adds grid inertia like hydro dam. So these two things are perfect for majority of scenario. And what's the penalty if you mess it up? Like, let's say you invested on something that is rather stupid. Well, if you are wasting money and time onto it, time and money will be destroyed, and it cannot be reclaimed. Once you burnt money away, it will never come back. Once you wasted time away, that really never comes back. So there is penalty for it. Like, you can delay your nation's energy independence simply because you are wasting money on some other place. You may not even think it that they could be collaborated, but they are. So we have to be very mindful. Now, first hype technology is FlyWheel. Now, FlyWheel, you may think, okay, it's a spinning mass, everything is cool, it will add grid inertia. Yeah, no, it's not synchronous. Almost no design uses synchronous. There are some systems, but these are more of stabilizers. Basically, they have a generator with a giant flywheel, and then they have a motor generator unit that is draining the energy. That point is just there to smooth switch over. It's not designed to as a energy storage. The moment you want it to act as an energy storage, you reach a point of where you have no longer control of synchronicity, meaning you cannot maintain the RPM. So it does not add grid inertia. Do not think that. So how do we deal with that? Well, you do not. You think in this way. You built a flywheel, cool, awesome. Flywheel spins up from 0 RPM to 100,000 RPM. Cool, it's 100% charge. What happens when you discharge it? It drops from 100,000 RPM to 0. So now you have a generator that is trying to extract energy. So a generator's hertz would be, let's say 400 hertz. It will drop to 4 hertz. Now you need what we call double conversion VFD, meaning you are taking frequency from your AC input is coming from one end, you are storing it into capacitor, converting into DC, and then you are making another sine wave out of it. You're getting sine wave in, but different frequency. You are sending it out on a different frequency. You're getting a variable, and you have to send out 60 hertz. It's basically job of a VFD, but again, it does add a lot of electrical complexity. It's not something that you can just it's complex, and it also wastes a bit of energy. And why it did not work, even though NASA worked on it and F1 actually used it. Now in F1, there was a bit of luxury they had, that they needed to store mechanical energy. So mechanical energy storage, it kind of worked. So the idea was this puppy from this end, when you apply brakes, it's gonna jack this puppy up into your crankshaft, leach as much energy as possible, and try to spin that puppy up through gearing system as fast as possible. Cool, awesome. Now that's during braking. That's, you are charging your system, draining energy. Cool, awesome. Now when the driver pressed accelerator, it will dump all that energy into the crankshaft, spinning it faster. But to it. Now it did work. It was used. It did work, but it's so convoluted and so messy that we were like, yeah, let's just yield this. We no longer use this. We are using batteries. And again, NASA also built all of the systems. Outcome is always the same. Battery is just better. And be my friend, if F1 with infinite money and NASA with infinite money, both of them worked and both of them have the same outcome, you can try to make it. It's just outcome will always be the same. Why the outcome is same? Well, high RPM is the problem. Now, RPM has categories. Easy RPM, who cares RPM, to stupid RPM. What is stupid RPM? Any RPM above 20,000 RPM is classified as stupid RPM. Because at that point in time, even ceramic bearing requires some special care to handle it. And if you do not want convoluted system into it, you have to pay the penalty of high friction. And again, you are talking about energy storage. You cannot have the luxury, oh, I dumped 1 megawatt hour into it. That 1 megawatt hour disappeared in 2 hours because of the bearing loss. So that high RPM is a very significant cost. The only way these things can handle it is generally trying to utilize what we call magnetic bearing. Only then you can have enough low friction, enough of a float system where it's like, okay, now we are not losing energy just because it's spinning. So again, you can have a vacuum pump that runs at that RPM, but again, it has a special bearing, super expensive, and because you are dumping energy into it, you do not care about it. It's just like, oh, bearing lost this much extra energy. Energy storage cannot do that. So high RPM causes that issue. Another is vacuum chamber. Even in these, they had vacuum chambers, and all the large ones, they need vacuum chambers, which I do not know if you know this. It's expensive, especially a vacuum chamber that does not leak when you are vibrating the hell out of it. So it's expensive. And then you have balancing the rotor. This costs far more than you think. Like, what if we make the rotor out of tungsten? Super easy. Take it and go. There are metal factories that like, oh, you want this? Damn, stamp it, take it and go. That's not an issue. Yeah, then you go to a company, it's like, okay, I want this rotor to be balanced so it can rotate at 100,000 RPM. Yeah, they're like, okay, bro, sit down. Give us a blank check. The end. That's the whole point. Balancing a rotor that can handle 10,000 RPM, minor inconvenience. Balancing a rotor for 25,000 RPM, ooh. Balancing a rotor for 50,000 freaking RPM, yeah, good luck. 100,000, yeah, that will take time. Like, that's not even like, oh, we have a machine that can handle it. No, it's gonna take time, sweet time, just to balance the rotor. So it becomes expensive. And can we balance all of this? Absolutely. It's just that you buy the money. So we have been there, tried it, outcome is always the same. So, and because of the very high self-discharge, yes, even with magnetic system, even with vacuum chamber, it still does not hold power for very long. Meaning even 4 or 5 hours is expecting too much. NASA tried it. So that's why FlyWheel, if anybody's like, we're gonna build FlyWheel energy storage, it does not work. Like, the biggest problem is that double conversion, and the fact is everything that goes into it is ludicrously expensive. Other person is like, what if we, instead of having that stupid RPM, we reduce the RPM? It's like, cool, awesome. Now your rotor is exponentially heavier in order to store same amount of energy. So we've been there, tried it, does not work. And thankfully, I've not seen anyone actually trying to do this on large scale. Then we have this CGI monstrosity, that is gravity battery. Now this is one of the most weird system because it has energy packets rather than energy flow. Meaning in FlyWheel, you dump energy, RPM goes up. You extract energy, RPM goes down. It's a very system. Same goes with pumped hydro. You pump water up, you drain water down. It's very smooth, continuous, meaning 0 to 100% can be drained in one go. It does not work this way. It works in this idea is you're gonna have basically blocks flatly laid out, and then you're gonna stack them like a Jenga blocks as up. That's your charging status. And when you need to discharge it, then you're gonna clamp the tall blocks and let it fall. So it's a gravitational system. Now, like, wait a minute, how much energy one block can have? Not much. That's the problem. It has energy packets. It does not have like smooth flow. Now, there were other company that was trying to convert mines into battery system, and their philosophy was a bit more better compared to the system because they were like, mines can be very deep. Some mines are kilometers deep. So they had that advantage, and the fact that they had one ginormous mass, and it can be like charge, discharge, fully discharged, fully charged. So they had a bit more smooth flow. This does not have smooth flow. This is not a smooth rider. So that's the biggest hassle with this. And it has way too many moving parts. Everything in this is moving parts. And I'm like genuinely shocked. Is like it needs great height to work. For example, if you are trying to do this in Burj Khalifa, it's awesome. 600 meters of height. That's GG. Even few tons will give you a many kilowatts hour of capacity. So that's awesome. But yes, it's expensive to make something 600 meter tall. So unless you have great height, it's not gonna work. Like, flat out, you need ginormous height. Concrete is dense, not that dense. That's why we use pumped hydro and so much of it. So to get that, philosophy is the same. You pump on the charging cycle and you drain in the discharging. So pump it up, drain it down. So you need great height. And again, it has too many moving parts. Like, this has every part. Be mindful, not only you have energy packet, because of all these parts, all the movement, it's gonna waste majority of it. Another aspect is, I have no idea how the heck in all CGI it just works. Dude, have you seen something known as Earth? Earth has something known as wind. The moment you add wind into this system, it's not going to be an automated system where it just works. It's going to need freaking AI and a magnetic system that allows you to actually clamp the bricks. You want to see example like a tall structure that is big, robust, crane-like. Starships. Launch tower, very big structure, big, beefy, designed to clamp it. Yeah, see, there are people who have zoom cameras and zooming into the top. It flexes. That ginormous structure flexes. Anybody who works with crane will tell you, wind is wind. You're gonna blow, my man. You're gonna blow. Now, again, that's why whenever people are working with cranes, they have people who are like, okay, guiding things down, people who are guiding things up. Otherwise, it will not work. So this automated system, I'm like, are they surrounded by mountain range where they are like, either A, it's very close to the ground, so they are stuck in a kind of turbulent dead zone. They do not have gust of wind because it needs a skyscraper shielding. Otherwise, it will not work. The wind will be a biggest hassle. So people are building it, and again, even Indian company Tata has started to invest into it. Chinese people are building it, the idea, and again, they have changed the design from this to this system where they have like a hundreds of unit small clamps, basically lift systems, where they're gonna discharge is drain, letting the blocks go down, and charging is pulling the blocks up. So many moving parts. I'm like, dude, this is bonkers. Thankfully, Israel has brain. They're like, okay, closed loop pumped hydro, shut up and take money. So this really is a weird idea. Actually, the company that is making this, now they just uploaded another video, and I was like, okay, what they are doing this? Yeah, they are using normal batteries now. So this really, I have no idea how the heck this got so much attention. It's like, have you heard of wind? Have you heard of the fact that we do not like energy packets? We want continuous energy. Energy packets is not a good solution. Then we come to another aspect, compressed air storage. This kind of made me lose hope in my country's education, because when I was talking about that graphite thermal energy storage system for power production, everybody's like, why don't we just compress air? We'll get 100% efficiency. I have no idea how the heck their education is this bad, but it is. So problem is compressed air hydrogen system, compressed air energy storage is old, like very, very old, many decades old. It almost touches the same point or actually crosses pumped hydro. That's how old it is. But problem is those were diabatic system, not adiabatic system. Meaning when you were compressing air, you had to dump lot of energy into it. Cool, you got compression, but what is the penalty? Not only you have air that is high pressure, but you also have air that is high temperature. And the whole mechanism, the compression heats up exponentially. If you want like hundreds of bars of pressure, it is brutal. It's brutally hot. So they had to vent that heat into the atmosphere. Okay, cool, awesome. But here's the deal, that's wasted energy. You wasted bonkers amount of energy. So 30 to 40% energy recovery was possible at best. And another problem was, once you have ludicrously high pressure and you are expanding it into a turbine, it started to freeze. And again, air has upper limit. Even if you can remove 100% of moisture out of it, if you have very high pressure expanding too much, you could reach a point where other gases start to condense. For example, carbon dioxide might start to condense. So they had to use natural gas firers. Basically, they are whoosh, going into the expansion system. Basically, oh, I have compressed air, expanding it, now you have a flame there. You actually needed natural gas to make the system work. So that was the biggest flaw of this compressed air system. Even though we have been using it, that's why nobody actually took it very seriously. Thankfully, adiabatic system have been developed. Now, idea is you're going to do the same thing. You compress this puppy hell up, but you leach the heat energy. You absorb the heat energy and store it into a heat soak. And once you need to discharge it, you have a high pressure air, you try to expand it. The moment you expand it, it drops in temperature. It's like the heat store at that point in time returns that energy. In principle, you can touch 70% efficiency, meaning almost at the same end as pumped hydro. So problem solved, right? Yes, if you have vast underground caverns. Now, can you store that amount of air in metal systems? No, not cost effectively. And again, from a geometry point of view, it's better to make one giant tank rather than hundreds of small bottles. But if you have hundreds of small bottles, it's far safer. But if you have one giant, it's far more economical. You see the paradox? And be mindful, the compression ratios we are talking about, the bars, basically, it's bonkersly high. If you have any failure, any rusting, anything, it will go vaboom. It's not gonna be like is going to be vaboom. So for that reason, underground caverns are the only way where you can store that much without costing too much. Let me be very clear, you can store it. Nothing in physics is saying you can't do that, you shall not pass. Nothing in physics is saying that, but everything in economics is saying no. So underground cavern, it makes sense. So you must have heard people are trying to do this in salt caverns, abandoned mine, abandoned oil gas, all those things. It will work. And it does require very complex, very expensive new infrastructure. Compare that to graphite thermal energy storage system. That's just copy paste one unit, replace one unit, pump this puppy in. Here it's a completely new system. Now it does make sense if as a country you have dried up oil wells, natural gas wells are perfect for this, salt caverns. Like if you have those geological features, this is good. This is good for you because majority of expenditure will happen in that energy storage part, compressed air part. Upper part is just heat storage because again, if it leaks, it cools down, not that big of a deal. It's not gonna go vaboom. So it can make sense if you have a lot of abandoned mines, lot of oil wells. In those scenarios, it makes sense, but it's not something like, oh, why not every nation do that? Every nation may not have this. It's almost like geothermal. So compressed air storage, it's also a flawed system, but again, does make sense if you have a adiabatic system. Anybody who's talking about non-adiabatic system, let it go. So it can be done. Then we have another system. They looked at compressed air system and they're like, what if we made it better? So the idea is you're going to take air. Instead of compressing it, you refrigerate the hell out of it. You convert into liquid, meaning you will have liquid nitrogen, liquid oxygen, and a little bit of argon and things of that nature. And then you're going to expand it. Now you have basically gas to liquid to high pressure gas, and that gas will run the turbine. Like, isn't that has the same issue of diabatic and adiabatic? Yeah, but to solve this, they have multi-stage thermal energy recovery system. So you take the air, you have to compress the hell out of it. You compress the hell out of it, you get compressed air, but you waste a lot of energy into heat. So that heat is hot thermal storage. In this scenario, either it's oil or water. They store that much energy into the storage number one. Then they refrigerate. Again, that also dumps a lot of energy. So that dumped energy go into high grade cold storage. It's rocks basically. So this leaching of energy in two stages: compression, energy stored; refrigeration, energy stored. Now you have basically liquid air at this point in time, and then when you need, this is how you charge it. All three tanks full up, that's charging. How much capacity, how much tank you have. And again, liquid nitrogen storage is far better than high pressure hydrogen, high pressure basically air, because again, that cracks, failures, kaboom. Here, psh, so it's far safer. Although it's hazardous for people, because again, if that much liquid nitrogen just vents out there, it might displace enough oxygen that people might, so there is a bit of hazard there, but not that much. So you store three components to it. So how do you get your energy back? You allow the liquid to boil. So you dump first a batch of energy from high grade cold storage. That allows you to boil. Basically, you go from liquid to pressurized gas. But again, it's not high enough where you can run turbine to run your generators. So that's the first stage. You get evaporation. But after that evaporation, you need to dump oomph to it. Now you utilize hot thermal storage. At that point in time, you have high pressure and high mass flow that runs your turbine, and voila, power out. So what's the benefit? Everything is compact, everything is above ground. So this is just a big warehouse kind of structure. You can store a lot of energy. Compactness is one of the things. It does not require geographical limitation of like salt caverns and all that. It is adiabatic, so it is good in that regard. However, there are a few things that is, even though this is older than the system that I am very excited about, it is very complex. Like, it sounds very easy. Oh, we're going to store this energy here, we're going to store this. You have three parallel energy storage system. Compressed air only has two. You have three energy storage. So it's complex. And cryogenic, while you may think, oh, stainless steel, not every stainless steel works. And be mindful, anything, exposure to liquid nitrogen is one thing. Staying there is completely different. Basically, bulk carriers that we utilize for liquid nitrogen transportation, all that, those are not same stainless steel. You have to have specific alloys, specific valves. Everything has to be cryogenically rated. That's not cheap. So not only you have complexity of three plumbing systems, you have cryogenic. So all of that costs a lot. And you need a new construction plant. It's not going to recycle your, oh, I have salt mines, I have this caverns that I want to recycle. It's not like that. Not like old coal power plants recycling and all that. So it does have serious penalty, and still does not give you very, very high, what we call round trip efficiency. You are looking at 50 to 70%. So it does work, but it's like, complex it is, and it breaks the kiss factor. Keep it simple, silly. This is not simple. So this was my presentation on some of the flawed energy storage system that we operate and what are their pros and cons. Hopefully you have liked it, learned from it. In that case, please hit the like button, share it amongst friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment, because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.